Hello, good afternoon, everyone. Could you please press the thumbs up sign if you can hear me and you can see the slide? Yes. Thank you very much. So welcome everyone to the Institute of Mathematics webinar series for this semester. Let me just remind everyone that this webinar is being recorded and it is being streamed live on YouTube, and the link will be posted on the Institute of Mathematics Facebook page. So by default, everyone is on mute. So if you have any question, just raise your hand, or you can also type it in the chat box. All right, so again, welcome to the webinar series for this semester. I am Gino Angelo Velasco, the coordinator for research of the Institute of Mathematics. So today we will be having two talks from the Mathematical Finance and Actuarial Science group of the Institute. So we'll be hearing from Dr. Luke Kevin Ong and Dr. Jasmine May Lui. Okay. So the first speaker is Dr. Luke Kevin Ong. He recently completed his PhD, and today he will be presenting his work titled On the Propagation of Chaos for Recombination Models. Okay, so let us all welcome Dr. Luke Kevin Ong.
Thank you, sir. Okay naman po yung audio ko.
Yes, Dr. Ong.
Okay naman. Okay. I-share screen ko lang po yung okay. Okay, again, good afternoon, everyone. My talk for our webinar today is on the propagation of chaos for recombination models. First, we will have a brief introduction on our study. Then we will discuss some definitions and concepts needed to present our results. The terminology propagation of chaos comes from CAP. In 1956, CAP investigated the probabilistic foundations of kinetic theory and introduced this concept for the Boltzmann equation. This has since then developed into an active field in probability. In particular, he was studying a stochastic process, modeling binary collisions in a gas made of a large number of identical molecules, and he was concerned with its rate of approach to stationarity. So what is propagation of chaos? Gottlieb wrote in his thesis that chaos propagates when the stochastic independence of two particles persist in time, as a number of particles tend to infinity. So why do researchers study propagation of chaos? Well, one motivation for the subject was to arrive at a connection between a detailed and a reduced description of the particle's evolution. Snitman mentioned in his paper that propagation of chaos deals with symmetric evolution of particles. That is, the study of one particle gives information on the behavior of the whole particle system. Other researchers include McKean, when he introduced this concept of interacting diffusions and analyzed what are now called McKean-Vlasov equations. More recently, Thai studied a discrete version of the particle approximation of the McKean-Vlasov equations, and she also proved the propagation of chaos property as well. So the previous authors are mostly concerned with proving that specific systems propagate chaos. One of the main goals of this talk is to present the propagation of chaos phenomenon for recombination models. What are recombination models? Rabinovic, and Sinclair stated that random matings occur between parental chromosomes via a mechanism known as crossover. That is, children inherit pieces of genetic material from different parents according to some random rule. Recombination models are probability distributions that represent this randomness. Caputo and Sinclair, on the other hand, stated that recombination models based on random mating have a number of applications in the natural sciences and play a significant role in the analysis of genetic algorithms. Moreover, they used quadratic dynamical systems to study the rate of convergence to equilibrium in terms of relative entropy for recombination models. Aside from physics and biology, the theory of propagation of chaos has other developments and applications, one of which include the theory of so-called mean field games, which was introduced by Lasry and Lyons. Their idea was to use the concept of propagation of chaos in statistical mechanics to derive models in economics and finance. So we now proceed with our preliminaries. We start by discussing the particle evolution of our particle system. We fix small n in the set of positive integers and define omega sub n to be the set of particles. Omega sub n is also known as the n-dimensional hypercube, where each particle is represented by an n tuple with each coordinate equal to either -1 or 1. For each positive integer, capital N, we also define omega sub n raised to capital N as our state space or our particle system. For simplicity, we will instead use omega for our notation. Each state S in omega is a set of capital N number of particles. We'll use the notation bracket n for the set of integers from 1 to n. Given capital A, a subset of bracket n, and sigma, an element of omega n, we write sigma sub A for the A component of sigma. That is the subsequence sigma sub j, where j is in capital A. We now define the recombination at a set. Given capital A subset of bracket n and the pair sigma eta in omega n cross omega n, the recombination of sigma eta at A consists in exchanging the A components of sigma and eta. This defines the following map, where AC is the complement of A, and the components of eta sub A sigma sub A complement is defined as follows. This means that if j is in A, then the jth coordinate of eta will remain the same. Otherwise, if j is not in A, the jth coordinate of eta will be replaced by that of sigma. We have a similar definition for the components of sigma sub A, eta sub A complement. For example, suppose n equals 5 and let sigma, eta, and A be defined as follows. Then by interchanging the second, third, and fifth coordinates of sigma and eta, we get the following. Let capital S be a state in omega where sigma upper I is a particle in omega sub n. Recombination walk on omega is a process that illustrates the evolution of an initial state S by applying recombinations on a random pair of particles at each step. We describe this process as follows. First, we randomly pick a pair K, L of distinct indices in bracket n, uniformly chosen from among all such pairs. Second, we choose a subset of bracket small n at random according to some probability distribution nu. And lastly, we update capital S by leaving sigma upper I unchanged for I not equal to K and L, and updating the particles sigma upper K and sigma upper L via the recombination at A. To illustrate, if we let R sub KLA of S denote the new state in omega, we have the following. That is, if we assume K less than L, the mapping R on omega is given as follows. Here are some examples of the probability distribution nu that we mentioned in the recombination walk. The first example of a recombination model is the single site recombination, where 1 is just the indicator function on subsets of bracket small n, as shown below. For this distribution, each singleton has probability 1 over n of being chosen. Other examples of recombination models include the one-point crossover, the uniform crossover, and also the Bernoulli-Q model. For the one-point crossover, we have each j sub I having the probability 1 over n plus 1. For the uniform crossover, each subset of bracket n has probability 1 over 2 to the n. And for the Bernoulli-Q model, we have a specific description as shown in this equation. We now discuss our Markov transition operator. So first, we let S sub j denote the position after the jth step of the walk, and phi be a bounded Borel measurable function on omega. To emphasize, the notation R raised to omega just means that phi is a function from omega to R. Let T sub Q capital N be the Markov transition operator on R to omega, represented by the transition matrix Q sub capital M. The function Q sub N phi is given by the following expected value, which is now equal to the following sum based on the process described by recombination walk. Here, the factor n taken 2 raised to negative 1 is present due to the choosing of distinct indices k and l from bracket capital N. Notice that applying R sub KLA twice on S will give us back S, which means that Q sub N is symmetric. That is, we have the following equality. Let P sub I be any probability measure on negative 1, 1 for I in bracket N, and let pi sub N be the direct product of the P sub i's. The product measure, pi, equal to pi sub n raised to capital N, gives us a reversible process, as defined by Levin et al., which we show below. This equality immediately follows from the definition of pi and pi sub n as direct products. And so we have the following equality for reversibility. Let Fn Sj denote the probability density of Sj. Then by definition of expected value, we have the following. But on the other hand, if we consider using the property of conditional expectations, we have the following equality. This is due to the fact that the quantity inside the outer expectation is just Q sub n phi of S. And since we have a symmetric Q sub n, this will imply that Fnj plus 1 comma S has the following form. Sorry, this is a typographical error. This should be S comma J plus 1 and then S comma J for the final equation. So, bale, una yung S doon sa last equation before the subscript J. Okay. So we now want to construct a time continuous process which will lead to a time continuous master equation. Here are our assumptions. The state of the process is now a function of time, S sub t, and the probability density, Fnts, is a function of the continuous time parameter t instead of the discrete jump index j. We assume that Fn of t plus dts only depend on Fnts and not on the past values. We also assume the probability that multiple recombinations occur in the time interval t plus dt is negligible. Thus, we have between times t and t plus dt the following probability that a recombination occurs. Here, lambda is just a constant. Since there are n particles, we have for dt the following equation. So that if we take the limit dt going to 0, we will get the following master equation, where I here is just the identity matrix. So this equation has initial condition Fn0s equal to F sub 0 n of S, which is our initial probability distribution. Moreover, we rescale time in such a way that we will get lambda equal to 1. So following the discussion of Carlen et al., we are able to get our time continuous master equation, that is a differential equation of the probabilities for the system at different states. We summarize the previous discussion in the following proposition. Let mu n sub 0 be the probability measure for S sub 0 with density Fn0 with respect to pi. And then for all t greater than 0, the probability measure mu nt for S sub t has density Fnt with respect to pi, where Fnt is the solution of the following master equation. Here L sub n is given as follows, and I is the identity matrix. The following definitions, which we will need, are adopted from Carlen et al. And Snitman. Given any probability measure mu n on omega and any positive integer k less than n, the marginal measure of mu n for the first k particles, which we denote by p sub k mu upper n of S upper k, is given as follows. We will use the notation omega upper k equal to omega sub n raised to k for simplicity. We now formally define chaos. Let mu be a probability measure on omega sub n. Let mu upper n from 1 to infinity be a sequence of symmetric probability measures on omega. That is, the value is the same no matter the order of the arguments. We say that mu upper n from 1 to infinity is mu chaotic if for each bounded function g sub k on omega n, we have the following, where g here is defined as the following product. In other words, chaos means that the marginal measure pk mu upper n approaches the product mu raised to k when n is very large. We now present our main result, the statement of the result in the following theorem regarding the propagation of chaos for recombination models. Let mu upper n be a measure on omega with probability density f upper n with respect to pi. Suppose that the sequence mu n from 1 to infinity is a mu chaotic family where mu is some probability measure on omega n. For each capital N positive integer, let fnt dot denote the solution of equation 1, our master equation, starting from the initial data fn. We let also mu nt dot be the measure on omega with probability density fnt dot, where mu n 0 dot is just mu n dot for simplicity. Then the sequence mu nt dot is mu t sigma chaotic, where mu t sigma is the solution of the following problem. Here mu sub a is given as follows. This result gives us now the connection between the master equation in equation 1 and this nonlinear differential equation in equation 3. As a remark from Horey and Mishler, suppose mu n is symmetric. We define the empirical measure of the system as follows, where capital sigma is a subset of omega n, and delta is the so-called Dirac measure. That is, delta is given as follows. Then mu n is mu chaotic is equivalent to saying that the following limit holds. Moreover, it is also equivalent to condition or the equation 2 with k equal to 2. To give an idea for the outline of proof of this of our theorem, we will state 3 lemmas that will be very essential to the proof. For the first lemma, this is on the convergence of the series that we will obtain from our master equation. So let G be a bounded function that depends only on a single particle. If capital T is less than 1/4, for any positive integer n, the following series absolutely converges for small t between 0 and capital T. The resulting value 1/4 is obtained when we are getting a bound for the resulting p series in the computation of for the proof of this lemma. So 1/4 is the factor that we obtain so that this series absolutely converges. For our second lemma, This plays a role in choosing the appropriate mu t sigma for our theorem. Let G be a function depending on sigma 1. Then for k positive integer, we have the following, where mu sub k plus 1, G sub 1, and G sub k plus 1 is given as follows by this recursive formula. And finally, we have the third lemma that will be essential to showing the chaos property in equation 2 for k equals 2. Let G1 and H1 be functions of a single particle, and let gamma sub 2 be a function of two particles, say sigma 1 and sigma 2, such that gamma sub 2 of sigma upper 1, sigma upper 2 is equal to G sub 1, sigma upper 1, H sub 1, sigma upper 2. Then again, for t between 0 and 1/4, we have the following equality, where G sub j plus 1, H sub k plus 1, and gamma sub L plus 2 are defined inductively as in equation 6. Many authors are concerned with proving that specific systems propagate chaos, which was first studied by Kapp. We introduced some definitions and ideas to prove propagation of chaos for a particle system where the binary interactions are represented by recombinations. Specifically, we showed that if a sequence of measures on our defined particle system is chaotic, then for t greater than or equal to 0, the sequence mu t is also chaotic, where each measure is obtained after applying recombinations on mu upper n for some time t. For future directions of the study, one can prove the uniform propagation of chaos phenomenon for recombination models. In this case, we do not fix t greater than 0, but instead prove the property uniformly in time. Here are my references. Thank you for your time.
Thank you very much. Let us all give Dr. Ong a warm round of virtual applause. Thank you. Okay, so thank you, Dr. Ong. Now the floor is open for questions from the audience. You may raise your hand to address the question live, or you may type it in the chat box. Sir Lu, ako po may question pala ako dun sa kanina. No? Yung sa future direction, ano, yung capital T.
Okay.
So you plan to have it uniformly. Pero kasi kanina, no, yung capital T natin, tama ba? Yun din ba yung sa less than 1/4 kanina? Or is it,
yes, sir. Nalimutan ko pala i-mention kanina yung sa 1/4. Bale, 1/4 yung length ng intervals, pero yung gagawin dyan ay pwede mo na siya i-extend by adding 1/4 and 1/4 until you get the whole 0 to infinity. Pero sir, hindi siya uniform eh. Parang ano pa lang siya eh. For a fixed small t, okay siya. Pero ang problema sa uniform, ang nabasa ko dito sir, kailangan ng Wasserstein distances in computing the distance between measures eh. So mas iba yung gagamitin.
Okay, kasi naging concern ko lang kung mag-aano siya na kung wala ba siyang bound or something that could that could cause problems dun sa ano, di ba? Just sa convergence or something.
Yeah.
So questions po from the audience? Okay, so how are we now with the... Sir Joma po, may question.
Yes, sir.
Hello, Clue.
Hi, sir.
And then dun sa, dun sa recombination models, yung sa procedure mo for the recombination, mga slide 9 yata yon.
Sige sir, wait lang ah.
May nabanggit ka kasi
Ito po sir.
na, yeah. So when you randomly pick the pair, uniformly chosen siya, di ba?
Yes sir.
May particular, ito ba yung reason, ito ba yung, can we use a different way to choose our pair?
Pag hindi, pwede rin sir. Ang mangyayari pag hindi equal yung chances of choosing the K and L, magbabago yung factor dito na sa expected
Dito.
value. Hindi na siya n taken 2 lang
N
raised to
taken 2.
-1. Pero sir, ang ano ko lang dyan ay baka, hindi ko alam kung ano yung magiging application pag biased na yung pagpili nitong indices. Kasi baka pwede naman nga sir na parang yung particles may iba talaga, mas malaki chance mapili yung ibang particle. Although hindi ko alam yung application kung
siguro lang kasi kunyari kung may external force
yes sir,
as an application, baka pwede yun magkaroon ng bias on
yes,
the
sir,
movement
pwede
of the particles.
Thank you. Kailangan lang natin i-tag kung anong particles talaga yung mga mas iba yung probability.
Right.
Yes. Thank you, sir.
Okay.
Thank you po, Sir Joma. Any other question from the audience? Okay, so kung wala na pong question, let us again thank Dr. Ong for that
Thank you,
nice
sir.
talk.
Salamat po.
And let us give him a warm round of virtual applause. Thank you. Okay, so before we continue with the next talk, we will have a 2-minute break. Okay, so we will come back. We'll see each other again at 2:36. Okay, so welcome back, everyone. Okay, so our next speaker is Dr. Jasmine May S. Lui. the Institute of Mathematics, and she will present her work titled A Study of Microcredit Repayment Delays in Southern Metro Manila, Philippines. So let us all welcome Dr. Lu. Dr. Louie.
Hello po, good afternoon.
Good afternoon, Dr. Louie.
Let me just share my screen po. Okay. Clear naman po ang audio.
Yes, audio is clear.
All right. Okay, so thank you po, Sir Gino, for the introduction. Good afternoon once again. For my lecture today, I will be sharing with you results of my PhD dissertation and some results on one study with one of my MS advisees before. So we have here a study of microcredit repayment delays in Southern Metro Manila, Philippines. So the first part is we'll be discussing the results on microcredit repayment delay. And then for the second part, we'll have a study of these delays in microcredit clients from Southern Metro Manila, Philippines. So what is microcredit? Microcredit is basically the provision of small amount of loans for low-income individuals. Borrowers do not have stable jobs, verifiable credit history, or even collateral. Hence, these borrowers do not have access to regular credit. Loans are also paid back in a short period of time with frequent installments. So this is one of the characteristics of microcredit repayment. So you have frequent installments. Usually, you have half a year or a year of repayment. And one of the main focuses of microcredit, or two of the main focuses, is on poverty alleviation, as microcredit services cater to small businesses and women empowerment. As you will see, or if you will check, most of the borrowers of microcredit are women. So the father of modern microcredit is Muhammad Yunus. He's the one who founded the Grameen Bank in Bangladesh in 1983. This bank give out microcredit loans to people or to borrowers in Bangladesh. Muhammad Yunus, together with this bank, received the Nobel Peace Prize in 2006 for his and the bank's efforts to help the poor. So, considering Yunus' example of microcredit, Mauck, in his paper, came up with what is called the deterministic Yunus equation. So this is based, just imagine you have 1,000 Bangladesh taka. One Bangladesh taka, for reference, is approximately 0.6 peso, Philippine peso. So imagine that you have to repay 1,000 Bangladesh taka in 50 weeks of 22 Bangladesh taka each week. All right. And so we are concerned, or he was concerned, with solving the actual interest rate involved, as we have to solve for the present value of these 22 payments that will equate to 1,000, or will equate to 1,000. So solving for R, which comes from Q star, will have the actual interest rate solved from this equation, and it's given by 0.19, or around 20%. Okay, so we can realize here is that microcredit has around this high of a rate or interest rate, 20%, around that value. Okay, so note that this value or this equation does not take into account the possibility that a borrower may have delay in repayment. So we considered what is called the generalized Yunus equation. This comes from a stochastic model of repayment, wherein we consider a Bernoulli process. This is basically a random variable equal to 1 when the borrower is able to pay at time M. Otherwise, it's 0 if the borrower is not able to pay on time. All right. And given this process, we were able to come up, or we were able to define what is called the random, or take a random sequence of random variables that represents random times when the payment is made, or when payments are made. So generalizing the number of weeks of repayment in a given year, letting n be the number of installments, and r sub f the flat rate. The generalized Yunus equation is given by this one. Okay, take note that in the deterministic Yunus equation, the flat rate is 10%. All right. Okay, so with this generalized Yunus equation, this time, this capital R here is now random. Okay, so we were curious, or we wanted to study or check how is capital R here distributed, or what is its probability distribution. Okay, so we made a few simulations. So this is just one, wherein we consider the in-time installment probability equal to 0.84. Well, in Malk's study, 0.84 is related to the 97% repayment rate in microcredit, which is just a default, or which is just a complement of the default rate, 3%, which is the internationally accepted default rate. Okay, so given if you fix n equals 50 and the flat rate 10%, we observe that the frequency distribution of this is, by the way, a Monte Carlo simulation of how many is this? 10,000 random repayments. So imagine you have 10,000 clients. Each of them might have a possibility of having delays in repayment. So this is the the distribution of the interest rate of those random clients. Observe that the histogram closely resembles that of a normal distribution, or a bell curve. But as we change the value of P, the histogram, or the figure, or the curve also differs. So if you're curious, you might want to check the study we made, okay, wherein we consider different values of P, right? We were also able to check for the histograms of the rates wherein you have specifically 1, 2, 3, and so on delays. Okay, I was not able to include it here, but given the histogram, you observe that the histogram for the case where there is one delay in those 10,000 borrowers, the histogram seems to represent a uniform distribution. Okay, so we tried to work on that and understand it better. So for having one delay, say you have delay at time or week K in this case, given n number of installments, the loan will be fully paid at time n plus 1, as there's only one delay, right? So using the generalized Yunus equation, it's like we'll just keep the payment at time K. Hence, we remove Q sub K, right, from the generalized Yunus equation. All right, and now we'll have here R sub K to denote the interest rate, or the effective interest rate, given the time delay at week K, or time K. So this is a lengthy proposition, but this just says that by the concepts, or by different concepts of non-standard analysis, if you've heard of infinitesimals and infinitely large numbers, we were able to come up with an affine function of the interest rate involved when there is a delay at time K, and it is in terms of K itself. All right. So here we came up with an asymptotic expansion of the of the effective interest rate of order 2. All right. And you will see that alpha sub 0 and alpha sub 1 are values dependent on the beta sub i's here, where the beta sub i's are defined as such. And alpha sub 2 sub k is clearly a function in terms of k. So here it was important, or it was significant, that we were able to come up with an explicit formula to identify the rate when there is a delay at time k. So upon getting this result, we were concerned on asking ourselves if the generalized Yunus equation can be applied in the Philippine setting. So yeah, before we go that, I just want to show you guys here. This is the plot of the approximate R sub case, the one using the asymptotic expansion formula shown earlier, versus the actual interest rate. Okay, when there is a delay at time k. The horizontal line here represents the rate when there is no delay in repayment. So observe that as the delay takes place at an earlier period in time of the loan, the rate is far from the expected interest rate when there is no delay. And as you go, or as the delay becomes closer and closer to the last payments or last installments, the rate, the rate goes closer and closer this time to the rate when there is no delay. So this came as a surprise to us, because you see how somehow linearly perfect the values are. Okay. All right. So in order to come up with results on trying to apply the generalized Yunus equation in the Philippine setting, we worked with one of the biggest microfinance institutions in the Philippines, ASA Philippines. It's a non-stock, sorry for the typo, non-stock, non-profit corporation established in 2004 by Kamrul Tarafder. It was known that Kamrul Tarafder got his training, I think, directly from the Grameen Bank in terms of microcredit. So as of the time when we wrote this research, ASA Philippines serves around 1,600,000 clients in around 1,100 branches nationwide. And I think it still applies up to now that they provide loans to clients at an interest rate of 12.5% to 15% for 6 months. So microcredit remains to be one, if not the most important services of microfinance institutions. So other services includes micro savings, micro insurance, among others. Okay, so you were able to successfully utilize the generalized Yunus equation in the Philippine setting. So loans in ASA Philippines are repaid in 23 weeks. So that's around 6 months or half a year. So we just modified the generalized Yunus equation. That is, we just we take n to be 23, right? And then we were able to come up with two asymptotic expansions for two cases. One is repayment without compensation, and the other one is with compensation. So here you see a similar figure for delays at time k without compensation. So what's the difference of this with compensation? ASA Philippines is very lenient in such a way that when a borrower delays at time k, for example, she or he is allowed to pay twice the installment for the succeeding week. Okay, so that's how compensation happens here. So with compensation, we observe that the rate is almost the same, or is almost the same for each value of k. Right? So it's like allowing compensation does not differ or makes the interest rate the same, right? Whether you delay at the first part or first parts of the loan period or at the end. Okay. The actual or the effective interest rate computed here is around 27%, right? Which is clearly higher than 20%. Okay, they say that microcredit interest rates are high because these interest rate amounts are used to cover all expenses, transactions, administration costs, and so on, right? Here. So, yeah. So, I and Mr. Samson, I believe is here. Hi, Gian. We were curious on what are the possible factors that affect delays in repayment here in the Philippines for microcredit. So there are only a few studies in Asia that identifies delays or factors that affect delays. So in the Philippines, little is known on the factors that could affect the existence of delays in repayment. Okay, so that's one reason for us to team up again with ASA Philippines, specifically in Southern Metro Manila. Due to logistical limitations, we're only able to look at 6 out of 9 branches in Southern Metro Manila. But I think there were around 230 or 240 responses, and randomly randomly chosen respondents are chosen, or were considered. All right. Yeah. So the main concern here is to check whether a client will have a delay or not. So in effect, we are trying to consider different factors in trying to identify if there will be a delay or no delay. Hence, our output variable is binary. Okay, so to be able to identify the factors, we perform logistic regression tests. Okay, so given y, the binary outcome, or the output variable indicating a failure or success, so of a delay, success of a delay and failure, we let that be small p, and let x sub 1 to x sub k be a set of predictor variables. Then the logistic regression y on these predictor variables estimates parameter values for the coefficients beta sub 1 to beta sub k via the maximum likelihood method of the following equation. This one. So this logistic function is just the odds, which is just basically the ratio of the probabilities of an event happening to that of it not happening. So it's just the probability that there will be a delay, or the ratio of the event that it will happen or there will be a delay to the event that it will not happen or there will be no delay. Right? So here we present the 19, if I'm not mistaken, 19 candidate predictor variables. These variables were or follows or adopted from a study of Nawai and Sharif in microcredit institutions in Malaysia, and in consultation with ASA Philippines, of course, these variables or factors were considered. Before we move on or before we perform a logistic regression test, it is important that we check whether these variables or a group of these variables are related. We want these variables to be as independent as possible. So one measure or one way to check that, what is called multicollinearity, is through the generalized variance inflation factors. I didn't include the definition anymore, but this just says that if you have a GVIF score of less than 5, then you may use the you may consider the factor. So as you can see, all the factors here, which by the way could either be continuous, which is linear, most of them, and some are categorical. So all of them have GVIF scores less than less than 5. Okay, observe that the highest value occurs at the variable or the factor of having a service job. But since this is clearly less than 5, we can still consider this in our logistic regression model. Okay. FYI, this research was done before the pandemic, so data were obtained using face-to-face interviews. Okay. Yeah. All right. And applying or running the logistic regression test on these 19 variables, it turns out that only 3 out of those variables are significant. All right. So here are the corresponding coefficient estimates in the logistic odds function. And this p-value represents the significance of the variable. At 10% significance level, if the p-value is less than 10%, well, in this case, lahat sila ay less than 10%, we can reject the null hypothesis that the coefficient estimate is 0. All right. So these 3 variables actually have an effect in delays in repayment. So the odds ratio here, basically, for example, for the dependence variable, if you have a dependent, say you are the client and you have a dependent, you are 1.17571 most likely to have a delay in repayment. So that's how we interpret that. So if a client has a job in service, say a family driver, a house helper, and then if a client has a job in the government, she or he is 2.5, around 2.56 and 3.13, respectively, most likely to have a delay in repayment. All right. But what we want is a balance between parsimony and goodness of fit. All right. Hence, we perform variable selection. So what we want is that our model describes our data satisfactorily, but at the same time, we have as few parameters as possible. So we try to select which of the 19 variables would really give us an accurate result in terms of predicting whether there is a delay or not. So we do that by using the Akaike information criterion and run what is called the stepwise AIC algorithm. The Akaike information criterion is just given by this value where L of theta sub hat or theta hat is the likelihood function of the maximum likelihood estimator, and 2 sub k is a penalty term. So note that this penalty term increases as more parameters are present. So as a rule of thumb, an AIC or a lower AIC gives you a better model, right? Yeah. And then performing stepwise, in particular backward stepwise AIC algorithm, we were able to come up with these 4 variables. So in the code run in our software, there were 16 steps. That is, we started at the initial model wherein all the parameters are considered. Then at each step, we subtracted or take one variable and then check for its AIC again, so on and so forth. If the AIC does not improve, that is, if we don't get an AIC lower than the previous AIC for the current model, then the model that we have will be the one that's optimal. Okay. So after 16 runs, the R came up with this 4 variables. Take note that these 4 variables have the same or have the lowest p-values when we ran the logistic regression using the full model or considering all the parameters. Okay, with these 2 variables having p-values less than 10%. As you observe here, the p-values for the variables other residents and dependents are greater than 10%, but we will keep these variables as they have intuitive relevance to delay. So as indicated by the negative coefficient estimate for the other residents variable, this gives us a hint or idea that if a borrower has another residence aside from his own residence, okay, this somehow indicates a better chance of repaying the loan. Okay, hence no delay could take place. And then the positive coefficient estimate for dependents say that as you have more dependents, okay, the likely is you will have the delay in repayment. Okay. So now that we have the AIC optimal regression model, we don't stop here. We now check if our model is valid. So how do we do that? So Gian, in his research, considered 3 values that will measure goodness of fit. Okay, so we have the Pearson and deviance residuals and the Hosmer-Lemeshow statistics. Well, these 3 tests, have something to do with the chi-square distribution, if you're familiar with it, which is usually used for goodness of fit tests. All right. These probabilities or the significance values, observe that they are all less than 10%. Okay, so what does this say? The null hypothesis of each of these tests says that you have a good, you lack fit. All right, let me just double check. All right, okay. So yeah, we'll see. So these values, hindi ko na po in-include yung definition, but you can check the manuscript. All right. This suggests, non-significant p-values. Just check. Yeah, sorry. These values these values are greater than 0.5. Yeah, 5%. The tests were done on a 5% significance level. I'm sorry. So yeah. Well, it will also be non-significant if you consider 10%. Okay, so all the tests here have non-significant values, which suggests that there is not enough evidence to reject the null hypothesis, which is that the model has good fit. Hence, we can consider or we can assume that the model has good fit. All right, sorry for the confusion. Okay, lastly, to validate our model or to check diagnostically if it's a good model, we measure its predictive power. All right. So what you see here is what you call the receiver operating characteristic curve. Okay. So basically, I won't get into much detail, but as you see here, this is a plot of specificity versus sensitivity. So this two has something to do with the true and the false rates. That is the number of, or the proportion considering the number of predicted ones to the number of actual observed ones or delays, okay? So on. This ROC, moreover, gives us the statistic called the area under the curve, or AUC, around, and it's calculated using R at around 64.6%. So this value, 64.6%, is considered in between 0.5, which is useless, they term it useless, and then the ones or the values which is acceptable, that's around, I think, 0.7 to 0.8, 0.7 to 0.8. Okay, so here we say that our model has 64.6% probability of predicting delays in repayment. Okay, so we see that even if it's between the useless and acceptable range values, we know or we feel that the study can be improved. Okay, so to further check if our model is valid, we did cross-validation. In particular, we did Monte Carlo cross-validation. Cross-validation, we do that because we want to take a look at how our model performs given a different sample, right? So this data or results that we have so far are results given our in-sample data. So we want to see or check how it works if we're given a different data or another data. So we use Monte Carlo cross-validation by considering 2/3 of our data to be the training set and 1/3 to be the test set. So we take these two sets. We take two sets. They are randomly generated. We do it, I think, 10,000 times. Oh, sorry. Ibang Monte Carlo pala yun. Yung kanina pala yun sa rate. We only do this, I think, I'm not sure. Yeah, 100 simulations, as we can see here. And we check the ROC, AUC, or the area under the curve, for each of the tests, for each of the runs. Okay, and the red line here represents the mean, as we take the average of the ROC AUCs here. Okay, and the indicated mean is at 63.26%. Okay. Moreover, we take or we run MCCV, okay, for each stepwise AIC run. The runs for, we take first the 19 variables up to only 4 variables. And we see here that the mean ROC or the value increases, which is a good indication of the predictive power of our model. All right, so as a summary, the generalized unit equation for microcredit can be utilized in the Philippine setting of microcredit. Data on microcredit repayment in Southern Metro Manila as a branches were studied, and we use variable selection by AIC to reveal and obtain 4 out of the 19 factors were significant in studying or in identifying delays in repayment. The Hosmer-Lemshow goodness of fit test among the other tests shows weak evidence of a lack of fit, hence a good fit. The model's predictive power via the MCCV was measured at 63.26%. So even, as mentioned earlier, even if it's greater than 0.5, we know that it can be improved. So how can we improve this? By possibly looking at different extensions of the study. First is by trying to look at transformations of the predictor variables, if there are any, and then possible we may consider other factors. Maybe we missed more, or maybe we missed some. One possible factor is to maybe consider how many delays happened or obtained or took place in the given loan period, because our delay here, the definition is just whether you have a delay, at least one, in repayment. And then finally, which is I think will be the best way to improve this research, is to consider a larger geographical coverage. Actually, we aimed at expanding or interviewing more people, because Southern Metro Manila is small for a nationwide study. But yeah, due to logistic limitations and then the pandemic, we weren't able to pursue. So we are curious on how the pandemic has affected microcredit repayment. So I think that will be a very good study. Okay, so here are my references, and thank you for your attention.
Thank you very much, Dr. Louie. Bigyan po natin siya ng masigabong
Masigabong.
virtual round of applause. Masigabong. Virtual na pala. Okay, maraming salamat po. Meron po ba tayong questions from the audience? Questions po from the audience. Actually, interesting yun, tingnan kung paano naging factor yung pandemic. Nabanggit niyo ba doon sa mga factors kanina? Meron ba na-reject? Kasi di ba may binabanggit kayo kaninang values? Nakapag-5 ba yun? Or kasi ang gusto niyo mangyari as much as possible independent yung mga factors, di ba? Tama ba?
Opo, sir.
Meron pa kayo na-reject initially?
Ay, initially po wala. Lahat po sila consider sa full model. Pero when we did the AIC algorithm, nag-reduce po siya into four factors. So out of the 19, 4 factors yung parang optimal na model na nakuha namin.
Okay. And another question of mine, doon sa pag-compute nyo kanina nung R at saka R, ayun sa mga RK ba yan? Yung meron kayong actual at approximate. Curious lang ako dun sa math nun, kasi meron kay approximation at may actual value. Meron din mga general error estimate yon na kapag nagko-compute ng gano'n dun sa microcredit, parang ina-expect na under certain conditions or factors na yung error between these. Kasi kung mapapansin, di ba, medyo malapit din yung mga nakuha yung mga values, tapos may increase yung increase.
Yes, sir. Actually, sir, ito po yung puzzling sa amin na hanggang ngayon hindi pa rin namin maisip kung anong dahilan. baka may interesado na habang lumalapit po sa end ng repayment period, sa end, lumalaki yung discrepancy, lumalaki yung error ng approximated values. So, yeah, yun pa rin po yung isa sa mga goals pala ng dissertation ko before. Pero definitely, sir, meron sigurong formula for this. Possibly baka pwedeng gumamit pa rin ng non-standard analysis.
Thank you. Do we have other questions from the audience? Questions po? Okay, so kung wala, good luck sa future research, o baka maging research thesis topic ng future students.
Yes, sir.
Kapag factored in na yung pandemic.
Yes,
so maraming salamat po. Palakpakan
Thank
po
you
ulit
po.
natin si Dr. Louie for giving this nice presentation. Okay, thank you. Thank you po. Okay, so that ends our webinar for today. And the next webinar will be on March 7, where we will be hearing from the groups, geometry and representations academic group. So until then, goodbye. So see you on March 7. Thank you everyone for coming, and thank you to the speakers. Thank you, Sir Joma Aden.
Thank you. Congrats.
So I'll end this now. Goodbye.